this critical level and you say, oh, you know, the coin is fair, okay? Again, I'm not going to bother you if you don't know anything about p-values, but I am only going to say, this is one test you do and the likelihood looks like theta to the 9th power, 1 minus theta to the 3rd power. So let's do another test. The same coin problem, but now I am going to flip the coin until I get I get 3 tails, basically. So when I get 3 tails, I stop and I say that's the end of the experiment. Before the end of the experiment was basically I'm flipping it 12 and I'm measuring how many heads I get. So now the end of the experiment is when I get 3 tails, all right? So when I get 3 tails, the data I collect is that I have 9 heads, okay? Do you know what distribution is that? When you do coin flipping until you get certain number of failures? Negative binomial. So if you search more, and it's in the slides, the details, effectively the likelihood looks identical minus some constant term. But if you calculate this p-value, which is the non-Bayesian way of making decisions if the coin is fair or not, basically your decision is completely different from the previous test, and as a matter of fact you say that the coin is not fair. So basically a non-Bayesian statistician, even though the likelihood is identical, will make a completely different decision from a Bayesian statistician. To be honest, and I have talked, of course, you know, I know lots of statisticians in my life, even those who are fanatic against Bayesian statistics, they are all working in Bayesian statistics now, okay? So it doesn't mean that there are no other ways of doing things, but effectively anybody who doesn't like Bayesian is left behind, way behind. All right, we're slide 21. Let's see, we're going to have to jump to slide 24. 24. I am only going to mention the bottom because, you know, we don't really have the luxury to philosophize. So you notice in the previous example that I demonstrated with the coin flipping, we decided when to stop the experiment. In one case, if we flip the coin 12 times, in the other if we get, you know, 3 tails. So the stopping rule principle says inference about a parameter theta must depend on the stopping rule only through the sample. So you cannot just say, I'm going to stop the experiment when the sun goes down or when this happens, etc. Only you can, if this is a function of your data and you stop based on the data, that's fine. Otherwise, you get in trouble. Okay? So this looks like again, a common sense decision, but the idea here is in Bayesian statistics, the data decide about your inference, not other rules that you introduce in the process. And I think I have another example, if I can find it, that is a very historical example. This is a nice example. Okay. So let's do the following scenario. We have a probability that x can take the value theta minus 1 or the value theta plus 1, and we assign the same value on these 2 probabilities. Okay, so this is our model, and we want to make an estimate for theta, and so my rule that I have here for estimating theta, this is my estimator. It's not a maximum likelihood estimator. I just postulate, you know, a common sense estimator. It says if I take 2 samples and they're not the same, then I'm going to take as my estimator of theta to be x1 plus x2 over 2. Do you agree with that? Does it look a good estimator? If the 2 samples are not the same, all right, so if one is theta minus 1, the other one is theta plus 1, don't you see that the average basically will give me theta? Nice. And it says now, if the 2 samples come to be the same, I'm going to take as my estimator of theta to be x1 minus 1. Now you notice that if it happens that your sample is theta plus 1, this works. But if your sample is theta minus 1, this gives you the wrong answer. So according to what you see now, without any data collected, how often you are right with this estimator? So you remember, you can have the following scenarios. The two samples can be different. So there are two cases like that, right? I mean, the first can be theta minus 1, theta plus 1, or theta plus 1, etc. Then both samples can be theta minus 1, and both samples can be theta plus 1. So what is the probability of going wrong with this model? 1/4. Okay, so 75% of the time you will do well with this model. Okay, now here is the idea. If you now are starting collecting data and you try to make some inference on the parameters theta, should you use the fact that this model is wrong 25% of the time? Should you bring on the table the fact that the knowledge, this is wrong 25% of the time? The answer is, if you're a Bayesian person, no. All right? The answer is, your inference has to depend on the data and nothing else. So once you say, this is what I do, this is my experiment, the data have to decide, your inference about theta. And this is what is called the conditionality principle. There's actually one of my friends from another university, not to mention, he loves to find paradigms on the other direction, where basically Bayesian inference gives you very wrong results, but actually they're sort of, if you don't have any data, if you don't have this, and if the universe blows up, then that's what happens, okay? But there are paradigms on the other direction as well. Okay, slide 27. We proceed, let's see. So we just stated this, so we don't need it. So summary. At least in the context of maximum likelihood estimators that we have seen, they satisfy basically the likelihood and the sufficiency principles that we discussed. Okay, so once you select an experiment, okay, all of those are satisfied, and basically the proof is on these two equations that you see there. We're jumping way down on slide 39, okay? And this actually would be a very easy slide, so I have to go very fast. So basically, the ingredients of a Bayesian analysis, either in estimating a parameter or evaluating a hypothesis, in this case age, will it rain today or not, all right? So they involve a prior model for your parameters and your hypothesis. They involve the likelihood that we discussed extensively on the last lecture. And of course, from those two, through the Bayes rule, you get the posterior. So the posterior is a distribution. It's not like a point estimate, like maximum likelihood estimate. It's a full distribution, and a full distribution is much richer information than just a point estimate. Okay? So again, you may ask me actually why I use all these different symbols, pi, f, and etc. And depends what book I was reading when I was writing these slides. Okay, the idea is, yes, we treat this as a function, so it's a good idea for the likelihood not to put a symbol for probability, and the same thing with the marginalization factor on the bottom that I'm going to come later on. But the prior, if you use a pi or a p, it's the same thing, okay? If you use something different in notation, it's also good, but you need to know what you're doing. Actually, I don't need slide 40. You know what I need? I need slide 43. So you may ask, is a full Bayesian analysis basically when we compute and use the posterior distribution for making decisions and inference, do they satisfy the sufficiency principle, and do they satisfy the likelihood principle? And let's pick up one of those. For example, let's take two likelihoods. that they differ by this function of x, c of x, and you compute the posterior, you notice c of x cancels in the numerator and denominator, because the denominator involves the likelihood, it's the marginalization is, the integral basically of the term in the numerator. So c of x and c of x cancel out. So basically inference through a likelihood f1 or a likelihood f2 gives